Hey again. Today we're going to be doing Le Chatelier's principles, and we're going to be talking about how his principles can determine, or how we can predict, how an equilibrium is going to shift, or how an equilibrium is going to change. So anyways, what his principles say is that in a closed system at equilibrium, is experiencing change, then there will be a process to counteract that change. So the way I like to describe it is that the reaction likes to do the opposite to fight the change. The reaction likes to fight the change. So here, our first change that we're going to look at to an equilibrium is a temperature change. So if the temperature, if the temperature is decreased, then the reaction will work to make the temperature increase. And here, if the temperature is increased, then the reaction will work to decrease the temperature. It'll do the opposite. So let's take a look at what is going to happen to this reaction. So what we have here is heat is decreased, and heat is energy. So we're going to be looking at an exothermic reaction. And so we have reactants making products plus energy. So if heat is decreased, this is decreasing. Now, if energy is being decreased, the reaction is going to try to do the opposite. The reaction is going to try to increase this energy. So if the reaction tries to increase this energy, the reaction is going to go forward. And then it'll make more energy, it'll make more products, and the reactants will decrease. So again, if heat is decreased, the reaction will go forward, will move in the forward direction, or what we say is shift right, okay? And it'll try to make more heat, more energy. And so when it shifts right, the products increase. And since it's going in this forward reaction right here, reactants are used to make this heat and to make products, and therefore we see the reactants decrease. And then it reaches a new equilibrium. So this would be our new equilibrium. Okay? So here's our old equilibrium and our new equilibrium. Now, let's take a look at if the heat is increased. So here we have energy is being increased. The energy here is going up. So what is going to happen is that if there's a lot of energy here, the reaction is going to do the opposite. So the reaction is going to try to use up that energy. So if heat is increased, the reaction is going to try to use up that energy and shift it left. So the energy is going to combine with the products, and it's going to make more reactants. And so what we see here is that it combines with the products and makes more reactants, and the reactants go up until it reaches a new equilibrium. And the products are being used up, and the products are going to go down until it also reaches a new equilibrium. Okay, so again, if heat is decreased, we're going to have one that looks like this, and if heat is increased, it'll be something like this. Now, if you had something that was a little bit different, instead of an exothermic reaction, we had a endothermic reaction. And so instead of energy being on this side, we have energy on this side. So if heat is decreased, this is decreased, then everything is going to shift this way to increase the energy, and therefore reactants will go up and products will go down. Okay, and if energy is increased, then the reaction will go left, shift left, and that means the reactants will go down, the products will go up, okay, until it reaches a new equilibrium. Okay, now let's look at the effects of concentration to an equilibrium. If a concentration of one species is added to an equilibrium, then the reaction shifts to use up that species. Again, if a concentration of one species is added, the reaction will do the opposite and try to use up that species and try to decrease that species that has been added. So let's take a look right here. What we have here is A has been added, so a reactant is added. So this one is going up, A is going way, way up. And what we see is, well, initially we add a whole bunch of reactants. So A goes up, and it just makes a very sharp spike, like this. And then it does the opposite. Then there's a very high concentration of A right here, and just like what we studied before in reaction kinetics, if there's a high concentration of reactants, well, the forward reaction rate is going to increase. And compared to the reverse reaction rate, which is relatively low, the forward reaction rate is high, and therefore the forward reaction rate is going to make this reaction go forward. Overall, the reaction will go forward, and therefore A will decrease. Now B will also decrease because it's going to go forward, and A is going to combine with B to make C and D. Now there is no spike on B because B was not added. Okay, A was added, and that's why we bolded it. And so A was added, so there's a sharp spike, and then it decreases. B, it just has a decrease. Now, C is a product, and since it is shifting to the right, C is going to increase. And D is also going to increase. Okay, and what we see here is that the reactants decrease and the products increase. Now A overall increase because we added some, but we can see that shift, that the reaction tries to do the opposite. Now here we have a product that is added, so D has been added to the equilibrium, and so D is going up, and what we see here is that the reverse reaction, there's a lot higher concentration of C and D, and therefore there's going to be a lot more collisions, and therefore the reverse reaction rate is going to be higher than the forward reaction rate. So overall, the reaction is going to shift towards the reactant side, or the reaction is going to shift left, and A is going to increase, and B is also going to increase. Now C is being used up, and therefore C is going to decrease. And D, well, we added a whole bunch of D, and so it went up, and then it shifts to the left, and so it decreases. And what we see here is, again, the reaction fights the concentration change. Now, let's take a look at what happens for a pressure change, the effects of a pressure change. So, again, if pressure is increased, then the reaction will try to decrease this effect. And this gets a little bit more complicated, but what it means is that if the pressure is increased, then the reaction will try to make less gases in order to kind of decrease that pressure. Now, pressure changes will only affect equilibriums with gases, which is very, very important. And let's take a look at this one right here. So we have 2A plus B making 2C. So this is two gases, 2A gas, and this is B gas, and making C gas. So if the pressure increases, then the volume decreases. So what I like to think of is that we are moving, our equilibrium is taking place in a box. And what is happening, the pressure is being increased. And what is happening is that that box that the reaction is taking place in just got smaller. Okay, so the pressure increased, or in other words, what we can also say is the volume decreased. So what we can also look at is how many particles of gas do we have here. So we have two A's and one B. So we have 3 particles of gas here, and 2 particles of a gas right here. So if the volume decreases, what we can say is that this is a smaller box and it's moved to a smaller box. What we can say is that we want to put smaller things into smaller boxes. Okay, so it's going to shift to the right because it has less particles and therefore less gas will be made. And another way you can think of it is that smaller gas, or a smaller volume of gas, will fit more easily in a smaller box. So everything is going to shift to the right. So what is going to happen to A, B, and C? Well, for the concentration, because this is concentration on this side, and what we can say is that the concentration of all of these is going to increase. Okay, so A is going to increase, B is also going to increase, and C is also going to increase. Now, the reason why they all increase is because, well, we're putting it into a smaller volume, the same amount of molecules into a smaller volume, and therefore our moles per liter is going to increase. So all the concentrations are going to go up quite sharply, and then since it is shifting right, A is going to decrease, and B is also going to decrease, and C is going to increase. Okay, so we see it shifts right, so A and B are used up to make C, and so A decreases, B decreases, and C decreases. And make sure when you kind of draw this to try to think about proportionalities. So when A decreases, it's going to be 2 particles of A is decreasing for every 1 particle of B. So this distance right here, this distance should be twice this distance from here. Okay, and this distance should be the same as this one, because for every 2 particles that this decreases, this increases by 2 particles. So these should be proportionately the same, the differences. Now let's look at what happened if the volume is increased. So volume is increased. So what is happening? What we're saying here is that a box is increasing. Okay, so the pressure decreases, or in other words, the volume is increasing. So what we have here is 2 particles, and it's going into 2B plus 2C. So here's 2 particles, and this is 4 particles. So even though the volume is increasing, well, in other words, so we're having a bigger box, and what we can say is big things fit into big boxes, and so therefore the reaction is going to move forward in order to make more B and more C, because that has a higher amount of particles right there. So A is going to, well, first, I guess what we should say is, since the pressure decreases and the volume is increasing, the amount of liters is increasing, and therefore everything is going to decrease in concentration. And then it's going to shift to the right, and therefore A is going to decrease further. B is going to increase, and C is also going to increase. Okay? And that is the effects of pressure change. So one of the keys is to figure out how many particles are on the reactant side and how many particles are on the product side, and then compare it, and then compare if it's going into if the pressure is increasing or the pressure is decreasing. Now, if you had something that is two gases here, and it forms an equilibrium and makes B plus C here, and this is two gases and two gases. Well, since there is no difference in the amount of gas and there's no difference in the amount of volume, there will be no change in the in any of it. So say if the volume decreases, if volume for this one, if we had volume decreases, what you would see is, if here was A, B, and C, and if volume decreases, therefore all of these would go up and then down, straight out. Okay, but there would be no change in the equilibrium. There would be no new equilibrium being formed. Okay, and the last one here that we're going to talk about is the effects of adding a catalyst. So a catalyst, as we know, speeds up the rate of the forward reaction and speeds up the rate of the reverse reaction. So it speeds up the rates of these forward and reverse reactions equally. If you remember here, if this was our activation energy, and this was if we add a catalyst, then what we see here is that the forward activation energy with the catalyst there is this high, and the reverse activation energy is, well, requires the same amount of potential energy, and it's going to speed up the reverse reaction rate as well as the forward reaction rate equally. It decreases them both by this much, and what we can say is, therefore, a catalyst will have no effect on a reaction that is at equilibrium. So what will happen is that this will just be no change, and same with this will be no change as well. Okay, and that's the effects of adding a catalyst.